Welcome to Unit 6, Section 3. In the last few sections, we've taken a look at properties of exponents. Today, we're going to take a look at exponential functions. So, functions that have exponents. An exponential function simply is a nonlinear function, and it takes on this form of y equals a times b to the x power. So you can see right there in our exponent is our variable x, where a represents the beginning amount when x is 0, and b represents the growth factor. Something can either be growing exponentially or shrinking exponentially. So first of all, a little bit of a difference. A linear function, remember, had a constant rate of change, whereas an exponential function has a constant percent rate of change. And this is what we mean by that. In example 1, we can see that our table of x's and y's are going up by positive 2 on the x's in between each little interval here, and positive 2 on the y's. So if we took the rate of change as change in y over the change in x, that would give us 2 over 2, which is equal to 1. And that's true throughout the entirety of the table. And if we were to graph it, it would look like this linear function. However, in example 1b, we can see that as we're increasing here on our x's by plus 1, we're not increasing by the same amount on our y's. We're actually going up by multiples of 3. So 1 times 3 is 3, 3 times 3 is 9, and 9 times 3 is 27. And that's what we mean by this constant percent rate of change. When we graph these points, we will not have a linear function, but instead we'll have an exponential function. It will be increasing quite rapidly or decreasing quite rapidly. All right, example 2 asks us to evaluate each function for the given value of x. Now keep in mind your order of operations, which says you need to do your exponents before doing multiplication, division, addition, or subtraction. So we want to evaluate negative 3 times 4 to the second power, which means we first need to evaluate 4 squared, which is 16, and now negative 3 times 16, which is negative 48. A common error people make is by multiplying negative 3 to the 4 to get negative 12, and then squaring negative 12, which would result in 144, and that's quite a bit different than negative 48. Example 2b, similar type of question. We've got y equals 2 times 1/4. I'm just going to write 0.25 as a fraction to the negative third. All right, handling our exponents first, we are going to simplify 1/4 to negative 3. Remember, we take the reciprocal of the base. Now that becomes 4 to the positive power. 4 cubed is 4 times itself 3 times, and that's 64. So this becomes 2 times 64, and the result y is 128. All right, a little bit about some of the properties of these exponential functions. Y equals a times b to the x has some similar properties, and it also has a couple of new types of properties. One type of property that it has is this thing known as an asymptote. Now, an asymptote is a line that the graph approaches more and more closely. In this case, it is always going to be the x-axis. That will be the asymptote of our general graph here of y equals a times b to the x. A is going to be known as the y-intercept, which, remember, we said that was also the initial amount. It's the beginning amount. And b is going to be our growth factor. All right, so let's try graphing y equals 5 times 2 to the x simply by plugging in some of these x values. Let's start with the easy one when x is 0. If I substituted 0 in for x, anything with the 0 power is 1, and 5 times 1 is 5. Remember, we said that that was going to be our y-intercept, and sure enough, there it is. How about when x is 1? That would be 2 to the first power, which is just 2. 5 times 2 is 10. All right, so that means if I go to the right one, I'm going to come all the way up here to 10. You can see it's already starting to increase quite rapidly. Let's go backwards to where x is negative 1. If we put negative 1 in for x, and we're going to show that to you over here on the right, then that becomes 5 times 1 over 2 to the first power. And that is 5 halves. All right, or simply written as 5 over 2. 5 over 2 is simplified to 2.5. So when x is -1, y is 2.5. All right, if we keep moving smaller to say to the -2, this becomes 5 times 2 to the -2 now, which results in 5 times 1/4, and that's 5/4. So that's slightly over 1. Again, that point exists right there. So a great idea for you would be to throw that into your graphing calculator and just look at the table of values. What you'll see as x gets smaller and smaller is that that number is really close to 0. That y value is really close to 0. And the graph of your curve looks exactly like this. So we say the domain of exponential functions, okay, y equals a times b to the x, the domain is going to be all reals. Our range, though, is only all reals greater than 0. Remember, this x-axis, and I'm going to highlight this in a different color, this x-axis right here is an asymptote. It's a line that graph approaches but never touches. Finally, our y-intercept here is when x was 0, our y was 5. Our asymptote, as we just said, was our x-axis. All right, we are going to skip over example 4. We'll tackle that one in class together, and let's scoot down to example 5. Here it says the graph represents bacterial population y after x days. We want to use the data here to find the population after 12 hours. After 12 hours and after 6 days. So let's see if we can just recognize our pattern of growth by taking a look at some of our y values and our x values. All right, so we're going to lay out our xy table, and we're going to say 0 days, there was 3 bacteria. 1 day, there was 9. 2 days, looks like there was 27. So on and so forth. It looks like we're multiplying by 3 here. So our constant rate of change, or our growth factor b, it looks like it's a multiple of 3. Now keep in mind our growth factor here is our b value in that general form of y equals a times b to the x. A represents our initial value, which occurs when x is 0, and it looks like that is also 3. So we could actually write the general form of this equation, y equals 3 times 3 to the x. Now we want to know what the population is after 12 hours. 12 hours is half a day, so that means evaluate this when x is 1/2. And we also want to find out what it is after 6 days. So evaluate this when x is 6. All right, so if we go to our graphing calculator now, we can go to our y equals, and we can plug in our formula here, 3 times 3 to the x power. And we can take a look at that graph, and we can see here it is coming along that x-axis and then shooting up. All right, so if we want to now find out what the number is on the 6th day, we can easily find that in our table. We can see what our population of our bacteria is on our 6th day here. It looks like it is 2,187. And if I want to find out what it is at the 12th hour, I can change my table by hitting second function, window, and having my table start at 0.5. Now, if I go to my table of values, I can see here at half a day, it looks like my bacteria count will be just slightly over 5. We'll round that down to make sense so that it's 5. All right, so keep in mind you could have evaluated those by hand as well by substituting those two values in for x. Here we're going to say our bacteria was 5 at half a day, and here our bacteria was 2,187. All right, in our final example for today, we're going to use our graphing calculator once again, and we're going to find an exponential model for the data set. So it says the table shows a rainbow trout population in the lake after t years. Use technology to find the function that fits the data. This means you're going to use the calculator to find a line of best fit. Predict the rainbow trout after 6 years. Okay, so we're going to go back to our graphing calculator now. Go ahead and press Stat and enter. Clear out whatever data that you have in your list by arrowing up to L2, press clear, then arrow back down again, over to L1, up, press clear, and arrow down. Okay, in L1 we're going to put our number of years, so that's 0 through 4. Okay, and in L2 we're going to put our trout population. Always do a quick double check to make sure your data looks exactly as it does on your page. Once you have that data entered in, now we're going to go back to pressing Stat, arrow over to Calc, and now we are going to scroll all the way down here past number 9, and we are going to perform what's known as an exponential regression because our population of trout are growing exponentially. So go ahead and press enter while the 0 exponential reg is highlighted. We're using list 1 and list 2, so we can cursor down and press calculate. All right, here is the exponential model for this data set. We see that we got y equals a times b to the x. Looks like our initial amount here is 31.24, and we're going to multiply that by the growth factor of 1.59 or 1. Yeah, we'll go to 1.59. All right, so let's go back to our page here. We got our model, which is y is equal to 31.24 times our 1.59 to the x. Next up, we want to find out what our population estimate will be here after 6 years. So that's evaluating this model for an x value of 6. So going back to our graphing calculator here, if we go out to our home screen here, we can type in our 31.24 times our growth factor of 1.59 and raise that to the 6th power. So a pretty good estimate then, it would be right around 504 trout.